Welcome to this explainer. Today, we're diving into a highly visual mathematical tutorial. We're going to see exactly how an automated spectral matching framework over the Adel ring offers a genuine pathway to proving one of the absolute oldest mysteries in mathematics, Goldbach conjecture. If you've ever wondered how abstract number theory connects to the continuous fabric of reality, well, you're in for a real treat.
All right, let's start with something we've all seen before, the familiar equation 2n equals p1 plus p2. It simply states that every even integer greater than 2 is the sum of two primes. It looks simple, right? But today, we're exploring how this discrete statement actually scales into an intersection of continuous Adelic data streams. We're going to look really closely at the exact mathematics that support this entire framework. Here's our roadmap for today. We'll hit the classical circle method, move into the Adelic generalization pipeline, check out the Rankin-Selberg convolution mathematics, dive into Satake parameters and density, and wrap it all up with the topological guarantee of continuity.
So, Section 1, the classical circle method. Take a look at how we can actually translate our traditional discrete number line into intersecting, continuous wave-like data streams. Under the unified hierarchy, to prove Goldbach's conjecture, the framework has to demonstrate mathematically that the total automorphic mass of these interacting prime streams cannot vanish for any even integer. The discrete dots literally become continuous geometry.
Let's really look closely at the math here. By examining these classical equations, we can see how primes are initially encoded as phases on a complex unit circle, using roots of unity. That's your generating function, s of alpha, right at the top. Below it is the representation integral r of 2n. This integral takes that phase stream, squares it, and extracts the exact number of ways to express an even integer as two primes.
Now, the absolutely crucial point in the classical method is how we evaluate that integral. It basically splits the circle into two parts, major arcs and minor arcs. Think of the major arcs as your coherent arithmetic signals, constructive interference near rational fractions. The minor arcs? Well, they're the rest of the circle, essentially turbulent, subleading, pseudo-random noise. Proving the conjecture classically means proving that the noise of the minor arcs doesn't wash out the coherent signal of the major arcs. Moving right along to Section 2, the Adelic generalization pipeline.
This pipeline here, this is our blueprint. We start at the top with our two prime data streams, but, and here's the kicker, instead of a simple exponential sum, we mathematically lift them via a von Mangold indicator into automorphic base forms on GL2 over the Adels. Then, through the Selberg trace formula, we fuse them into a tensor product L function. This quantized phase alignment mathematically ensures a non-zero intersection, leading us straight toward a proof where r of 2n is strictly greater than 0.
Okay, Section 3, Rankin-Selberg convolution mathematics. Pay attention to this global integral, I of s. It acts like an automated arithmetic detector. Instead of manually slicing up a unit circle into major and minor arcs, we project our prime indicator functions directly onto two cuspidal automorphic representations. As the unfolded equation below shows, the global integral perfectly unfolds into a Dirichlet series. That is the global Rankin-Selberg L function, capturing all that correlated prime data in one unified mathematical object. And this brilliantly illustrates our translation dictionary between the two worlds. I mean, look at how perfectly they mirror each other. The classical major arcs literally become the analytic poles of the L function at s equals 1. And that messy minor arc noise, it's mapped entirely to the behavior along the critical line where the real part of s equals 1/2. Even the singular series translates perfectly into an Euler product of local Satake parameters.
But, just mapping the noise isn't enough. We actually have to control it. To mathematically guarantee that the pseudo-random minor arc noise cancels out destructively at high frequencies, we must establish this exact subconvex decay rate. We have to prove the L function is strictly less than the conductor to the power of 1/4 minus delta. Breaking this convexity barrier is what ensures the noise cannot overwhelm our major arc main term.
Which brings us to Section 4, Satake parameters and density. Enter the Satake parameter matrix. So how do we keep count in a continuous space? Instead of discrete counting, prime density is converted into the continuous complex variables of this diagonal matrix, sitting right inside the Langlands dual group. The specific diagonal entries, alpha 1p all the way to alpha np, capture the exact behavior and density of the prime data stream at each individual prime place. And here is the exact translation of that arithmetic density. By taking the logarithmic derivative of the local L function, we reveal this amazing relationship. The arithmetic weight of the prime stream perfectly maps to the trace of the powers of this matrix. For example, at the prime count level, where m equals 1, it maps exactly to the trace of A. The math beautifully converts a discrete prime count into a matrix trace. But these parameters can't just be anything. Actually, scratch that. They are strictly governed by generalized Ramanujan constraints, which acts as a massive mathematical anchor. The first rule, the unitary anchor, ensures the matrix parameters stay locked to the unit circle. And because they're locked, the trace is strictly bounded, which brings us to step 3, preventing density gaps. This rigidity ensures the global prime density never just drops out or clusters irregularly. Finally, let's jump into section 5, topological guarantee of continuity. Here, the classical counting function is completely reimagined as a localized scattering event. Notice the integral of topological fields across the dual prime variety. In this field-theoretic view, the integer 2n is actually a targeted spacetime translation coordinate. The primes are acting as generative data streams that are quite literally stitching together the continuous geometric fabric of emergent spacetime. So we have to ask the big counterexample hypothesis. What happens if Goldbach's conjecture fails? What if, just imagine, the minor arc noise perfectly cancels the constructive residue, causing the intersection mass at a specific coordinate to equal exactly 0? Is localized total destructive interference mathematically and physically possible within the Adelic framework? Well, if it were possible, the results would literally be catastrophic. Let's break this down into 3 steps. Step 1, total destructive interference at coordinate 2n. Step 2, this would force the generalized prime variety volume to collapse to absolute 0. Step 3, this localized collapse creates an unsmoothable singularity. We're talking about ripping an informational vacuum void directly into the spacetime continuum. The entire global metric would completely shatter. Thankfully, spectral projection theory steps in and provides a massive contradiction. Our mathematical anchor, those unyielding unit circle constraints of the Satake parameters we just talked about, they mathematically forbid these local density deformations. For r of 2n equals 0, the local traces would have to drift completely outside the unit circle, but the rigorous trace bounding forbids it, meaning this space-time rip is impossible. No way it happens. And that gives us our automorphic guarantee. Because global Hecke operators act as topological stabilizers, distributing phase vectors uniformly, the major arc poles will always inject a massive baseline of constructive interference. This baseline mathematically overwhelms any bounded continuous noise. Therefore, the intersection mass cannot drop to 0. The conjecture mathematically and robustly holds. It leaves us with a truly profound realization to ponder as we wrap up this explainer. Is the continuous, smooth fabric of our universe entirely dependent on the unbreakable truth of a discrete arithmetic puzzle? It turns out, Goldbach's conjecture is not just some isolated math problem, but it's the precise algebraic safety net keeping the fabric of spacetime perfectly and continuously intact. I really hope this visual journey through the Adelic Langlands framework has totally changed how you view prime numbers.